Drop a like and do share. Leave your comments and do not forget to subscribe for more videos.
Hi everyone, welcome back to the course on Introduction to Material Science and Engineering offered by Edupedia World. Previous lecture we discussed about slip and slip system. Today we'll study about strengthening mechanisms. From previous lectures, what we understood was that in order for deformation to take place, we need dislocation motion, right? So if by some mechanism or by some method we are able to make the motion of dislocation difficult, then what we can do is we can increase the strength of the material, right? Because now to move the dislocation, thereby to cause deformation, we will have to apply more stress. Okay, so let us see the different strengthening mechanisms that are there. What we'll study in the upcoming lectures are grain size reduction as a mechanism, solid solution strengthening, strain hardening, precipitation and dispersion strengthening, transformation hardening. These are the different methods for strengthening mechanisms that are generally used, and we'll see all of them shortly to understand what each of them mean. And as I said, the idea is basically to provide hindrance to dislocation motion, because movement of dislocation leads to deformation. If dislocation motion is restricted somehow, then deformation will be slowed down, or more amount of energy or more amount of load or more amount of stress will be required for the deformation to take place. Now let's see each of them shortly before jumping into detailed description. Grain size reduction is what will happen is that there will be grain boundaries which will restrict the dislocation motion. So this is basically grain boundary. I will be writing what are the factors which are affecting the hindrance to dislocation motion, thereby increasing the strength. Solid solution strengthening is solute dislocation interaction. We'll see in details, but basically what is happening, the solute and dislocation will interact, and that will try to hinder the motion of the dislocation. Strain hardening is basically creation of lot of dislocations, thereby there is dislocation interaction. Okay, and dislocation interaction leads to reduction in the movement of dislocation or difficulty in the movement of dislocation. Precipitation and dispersion strengthening are, there are precipitates formed or dispersed particles throughout the material, and those things restrict the dislocation. So basically physically restrict the dislocation motion. Transformation hardening is a completely different mechanism. That's not exactly a restriction to dislocation motion, so we'll see that later. Let's start our discussion in details with grain size reduction. So as we have discussed in the previous lecture, that the grain boundaries are sites where dislocation motion is restricted. In the case of polycrystals, as I discussed in the previous class, suppose we have something like this, and the slip plane, let's say, is in this direction, and over here is in this direction. So the dislocation which is moving in this direction, on coming at the grain boundary, it kind of gets restricted because the slip direction is not the same in the adjacent crystal. So there has to be a buildup of stress over here, so that this dislocation which is at the grain boundary is either pushed into the next grain, or the stress becomes so high over here that leads to generation of new dislocations in the adjacent grain. So that increase in stress is what is leading to strengthening of the material. Now imagine that you have two scenarios. In one scenario you have really large grains, something like this, and in another scenario you have very small grains. Okay, so what will happen is that in the second case the dislocation will keep on encountering grain boundary after very small distances. Okay, as a result much more amount of energy or much more amount of stress will be required for the dislocation movement from one end to another. It will be much easier in the case of larger grains. So what is happening basically is by decreasing the grain size, we are increasing the number of hindrance per unit length for the dislocation. Thereby, by decreasing the grain size, we are increasing the strength of the material. Okay. Point to note is here is that high angle grain boundaries are basically where the dislocation cannot penetrate from one grain to another. So for high angle grain boundaries there has to be dislocation accumulation in grain number 1 such that the dislocation accumulation leads to so much stress that there will be generation of grains in grain number 2. So stress concentration leads to activation of dislocation in the adjacent grain for high angle grain boundaries. For low angle grain boundaries, the dislocation can actually traverse from one grain to another grain, but in that case too there has to be sufficient stress for the grain to be pushed from one side to another side. But say this will be a less effective method to increase the strength, because obviously small angle grain boundaries means small mismatch. So it will not be very difficult for the dislocation to move from one grain to another grain, but obviously it will also provide strengthening mechanism. Okay, now the exact relation for the grain size reduction leading to increase in strength is given by what is known as Hall-Page relation. What does Hall-Page relation say? Hall-Page relation states that the final strength is initial strength, this is constant, this is a particular initial strength, plus a constant times inverse of square root of grain diameter. This is grain diameter, average grain diameter, grain dia. So smaller the grain diameter, larger will be this term and more will be this term, and thereby the decrease in grain size leads to increase in strength, yield strength of the material. But one thing to note, that this Hall-Page relation, though it holds good for microscopic scale, it fails at very small grain size or very large grain size. So this is normally used in micro range. Okay. One interesting feature of grain size reduction method to increase the strength is that this is one of the only method which both increases the strength as well as the toughness of the material. That is, it increases the strength as well as the ductility of the material. The other methods that we'll study, those methods leads to an increase in the strength of the material. There is a compromise by reduction in ductility of the material. Since grain size reduction leads to improvement in both the properties, this is a very good method to increase strength and very preferred method. The problem is you can only reach a particular amount of strength by using this method. So you actually need other methods if the strength requirement is more than that can be achieved by grain size reduction. Okay. The second method to increase strength is known as solid solution strengthening. What is solid solution? Solid solution is basically you have a metal and you alloy that with different kind of atom. Okay, so there is a alloying with impurity atoms. So if you have iron, and let's say we have iron, we alloy it with, let's say, carbon atoms. Okay, so there will be carbon atoms spread throughout the iron matrix. There will be carbon atoms present. Now what this will do is that carbon atoms, the solid solution will provide strain, the lattice will be strained, and we know that dislocations are themselves also strained regions, that is, they have strain associated with them. Therefore what happens is, suppose there is a region of compressive region, compressive strain due to the alloying element, and the dislocation reaches somewhere like this, which has the tensile region and the compressive region of the solute and the tensile region of the dislocation matches, then the dislocation will be kind of pinned down over there. It will require much more energy to remove the dislocation any further from the solute particle. Vice versa, if the compressive region of the dislocation and the compressive regime of the strain due to the solute particles come close, they will repel each other, thereby the dislocation will again be, it will be difficult for the dislocation to move. So either there is a pinning down of the dislocation or there is a repulsion of the dislocation, and these both methods leads to an increase in the stress requirement for the dislocation to move, thereby the strengthening takes place by solid solution. The alloying impurity atoms leads to strengthening. Okay, the increase in strength and reduction in ductility is the resultant of solid solution strengthening. The strain field dislocation interaction, this is basically what I already discussed, that if we have a dislocation here and if we have solute particles over here, then this solute particles, since there is the extra half plane missing here, this solute particles would like to go there, and this will pin down the dislocation, thereby the dislocation will no longer be able to move. On the other hand, if the dislocation is coming close to solute particles over here, then it will actually be repelled and the dislocation can no longer move in this direction. So this strain field due to the solute particle and the dislocation interaction leads to solid solution strengthening. Let's recap. What we saw in today's lecture, we saw the different kind of strengthening mechanisms that is possible to increase the strength. We discussed about grain size reduction, how reducing the grain size leads to increase in strength, because more number of grain boundaries means more restriction to the dislocation motion, thereby increasing in the strength. We have seen the solid solution strengthening, that the solute particles kind of pins down the dislocation or they repel the dislocation from moving further. So this gives you an idea about the different possible ways in which strength of material can be increased. Next lecture will further drill down into the other methods of increasing the strength of a material. Till the next lecture, have a great day. Goodbye.